Welcome back, everyone. Today we're going to continue our work with conic sections. Today you're going to learn about a new one called an ellipse. As discussed before, we talked about how a conic section is any intersection of a plane with a pair of cones stood tip to tip. We talked about circles last time. Today we're going to introduce you to ellipses. We'll stay on this for 2 days and then we'll move on to hyperbolas, which is this shape right here. Basically, an ellipse is a non-symmetric circle. So it is what defines its shape is a major radius and a minor radius. So it's going to have a long radius in one direction and a shorter radius in another direction. The official definition of an ellipse is slightly more technical. It is the set of all points where the sum of the distances between two fixed points is constant. So what that means is if you add up the distance along these dotted lines right here, any of them, the distance traveled along that dotted line is always the same if you're inside of an ellipse. Or another way to think about it is if you put 2 nails in a board, tie it together with a string loosely, and then just trace the shape that you can with a pencil inside of that string, you'll end up with an ellipse. Now, if we look a little bit more in detail to these ellipses, you'll see a couple new vocab words. So technically it doesn't have a corner, but we still call it a vertex, just like we would with a parabola. So it's got 4 vertices all the way around. It's got a set of major vertices, and it's got a set of minor vertices. And then these 2 points that are considered the fixed points through their distances are the same. We call those focus points, or plural is foci. And then of course we have a center, just like we would with a circle. Now, last time I alluded to the fact that a lot of conic sections have actual real-life applications. I just wanted to share a couple about ellipses. There's a few buildings out there in the world that are dome-shaped in an ellipsoid. So what they do is they take an ellipse right here and they rotate it about the x-axis, and it creates this 3-dimensional ellipsoid shape. And what happens is if you are standing here and another person is standing there, basically any sound that you generate, the other person can hear as if they were standing right next to each other, even though this distance right here may be several hundred feet. If it's a well-constructed building, the sound will basically just reflect off the walls and you'll be able to hear it over there. Another application of an ellipse in the medical field is lithotripsy, which basically they shoot a beam of something, but they focus that beam on any particular thing inside of a human body that they want to destroy. I'm sure they can do this with chemo too, but it's basically you create a source of whatever radiation you want to shoot at whatever object. And what it does is one side of it acts as like a lens and it shoots the beam of whatever at the target. If this were completed as like a full shape here, it's an ellipse, so it will focus down to another focus point. So it exploits the fact that there's a focus where you can spread a source of whatever, and it can target a thing at a second focus point. All right, let's go to the math of it. Basically, an ellipse is a squashed circle. We've done a variety of function transformations before where we've applied horizontal and vertical stretches to a function, and it's basically the same thing here. We're going to take a circle and multiply it by a factor to squish it either in the horizontal direction or the vertical direction. And it goes a little something like this. So say we start off with a circle. That's always centered at 0, 0. So if we just shift it off to a center of hk, then we get that equation, and this point would be hk. Now, if we wanted to squish a certain dimension of it, everything in this term has to do with x. That's everything horizontal. This term has everything to do with y. That's everything with vertical. So if we add a term through division, not multiplication this time, but through division, we can create a shape that is longer in one direction than the other if we choose different numbers for a and b. A standard practice when we're talking about ellipses is so that when we name things a or b, we can switch which one is a and b, but a is going to always be bigger than b. And the reason for that is it's going to define, if a is bigger, that's going to define that the radius in the y direction is biggest because the a is with the y term. So ultimately our formula for an ellipse ends up looking like this. The one rather unique thing is the right-hand side of the equation is no longer a radius because it wouldn't make sense to have a third radius. So we have a horizontal radius, a vertical radius, and then we're just going to set this side of the equation equal to 1 just to be in kind of a standard form. We still have an hk for our center, and this ends up being our vertical radius, and that ends up being our horizontal radius. Now if we switch a and b, we get a slightly different variation on the same equation. So remember, a is bigger than b, so if a is on the x term, that means that the ellipse is going to be longer in the horizontal direction. If a is on the y term, you can see that the y's and the x's change places here on these equations. If the a is on the y term, that means that the ellipse is going to be taller than it is y. The long dimension of the ellipse is referred to as the major axis, and the short dimension of an ellipse is referred to as the minor axis. Now, as I talked about before, there are two focus points inside of every ellipse. So if we have this equation right here, we have our, in this case, our vertical radius is b, so you can see that right here. Our horizontal radius is a, so you can see that distance right here. But the other important distance is the distance between the center to the focus. So it's really important that we be able to find these focus points. And these three distances are related in a equation that's very similar to the Pythagorean theorem. So assuming that a is bigger than b, we got a squared minus b squared equals c squared. So it's Pythagorean theorem with a subtraction symbol in there instead. And the thing that you need to get out of this formula is that a, b, and c are all distances that are measured from the center. So once you know your center, you can go in the vertical radius direction, you can go in the horizontal radius direction, and then whichever is the major axis, that's the axis that you'll find your focus on, and you can just step out whatever the distance is c to the focus. Now obviously if you calculate a focus that is outside the ellipse, you've done something wrong, so that's a self-check that you can do. Additionally, we can take this formula and we can solve this for c. So if we take all the formulas that we have so far, so this is the variant where it's longer in the x direction as shown, or this is the variant where it's longer in the y direction not shown. We have two standard form equations for an ellipse, and then we have this equation here that will help us calculate the foci of the ellipse. And if we wanted to solve it for just the distance c, we could do this. If we just throw an absolute value bar around a squared minus b squared, you can calculate c in one step. So even though it's a relatively simple looking shape, we've said a lot of words and there's a lot of vocab to go along with this very simple shape. So this is kind of a summary of all the vocab that might come up during the process of a problem. So here's the center. Major axis is the long one. So in this case, it's the y-axis. And in this case, it would be the b value. So in this equation, a is actually smaller than b. So this is breaking convention just in this general equation right here. The minor axis is in the x direction because the a is associated with the x term. Horizontal radius is just a. Now notice that in the equation it shows up as a squared. So if you see a 16 there, then you know that your horizontal radius is actually 4 and so on. And then if you want to find the foci, you can calculate this distance and you can count out that from the center along the major axis. So let's try one. Why don't you pause the video, write down this equation, draw yourself a quick set of axes so that you can graph this with me. The first thing you have to be able to do is interpret this equation the same way that you would need to interpret a circle equation. So you need to be able to look at that, say, what's the center, what's the horizontal radius, what's the vertical radius? And you can also immediately tell in which direction it's longer. Now you can see that there's a larger number here, 9, which means it's going to be longer in the x direction. So this is going to be stretched left to right, larger than it is up and down. So our center here, it's the same as we would do for a circle. So -2, 1, and then our horizontal radius is the square root of that number, which would be 3, and our vertical radius is the square root of that number, which would be 2. So we can know those three pieces of information. Once we know those three pieces of information, we can actually graph the ellipse itself. So what I'm going to do is I'm going to plot the center, and then I'm going to go up and down 2 and make a dot. And then I'm going to go left and right 3 from center and make a dot, and basically sketch in the curve between all 4 dots, just like we did with the circle up, down, left, right. But this time the up, down, and the left, right distance that you travel from center is different. The other thing you're going to be asked to do pretty much with every problem is find the foci. Once we know our horizontal radius and our vertical radius, this is A, this is B in that equation. So the longer radius and the shorter radius. So we can use that a squared minus b squared equals c squared formula. So we just plug in our numbers right there, solve for c. We get 2.2. Now that means that I'm going to travel from this point 2.2 out to the right and 2.2 out to the left. Put a dot there. And to find those coordinates, basically you take your x coordinate here, subtract 2.2, and add 2.2 to get there. Let's do another one. Pause the video, copy down this equation, and give yourself a plotting area. Okay, you may notice that this one doesn't look exactly like standard form, but we can fix that. Remember, you're allowed to draw a 1 under anything, so we're going to think about that as x plus 5 squared over 1. And that would mean that our center is at x coordinate -5. Now this doesn't have a plus or minus binomial in there at all, so that must be a plus 0. So that means that we've got -5, 0. Take the square root of that for our horizontal radius. Square root of 1 is 1. Square root of that is 7. So if we put all that information together, we get that. Our center -5, 0, horizontal radius of 1, vertical radius of 7. So tall and skinny, we can go ahead and draw it. So I plotted my center, and then I went out 1 unit to the left, 1 unit to the right, 1 unit up, or 7 units up, 7 units down, and then we can go find our foci by using our Pythagorean theorem lookalike formula. And our larger radius is 7, our smaller radius is 1, so we go 7 squared minus 1 squared, so that would be 48. And the square root, 48, not 78, that's a typo right there. But once you take the square root of that, you do get 6.9. Now that's going to be really close, tight up into this corner, but that's actually fairly typical when you're graphing these, so don't be freaked out that you're way up in the corner there. That's very typical. Unless your ellipse is more round than it is skinny, you will have that situation happening. That's it for that one. Let's move on to the next. Go ahead and pause the video, write down that equation, and give yourself a plotting area. Okay, this one is for sure not in standard form. We notice we don't have any denominators, and the right side of the equation is not 1. So we're going to kill 2 birds with 1 stone. We want to get this to be 1. That's basically your only goal. You don't even care what numbers these are. Hopefully it'll work out to something nice, but we just need that to be 1 because that's a major convention in the standard formula. So we're going to divide every single term by 36. And then you notice that I have 4 over 36. So we're going to treat that like a fraction. 4 over 36 would be 1 over 9, and 9 over 6 would be 1 over 4. So that ends up being y minus 3 over 9 and x plus 2 over 4. Now be very careful here. They've listed the y term first, and it is longer. So this is a tall and skinny ellipse. So our center is at -2, +3. Our horizontal radius is the square root of 4, which would be 2, and our vertical radius is the square root of 9, which would be 3. So we get that information in there. We can go ahead and plot it just like we always did. And now we need to calculate the foci. So there's our long one, there's our short one. Go 3 squared minus 2 squared equals c squared. That will get us 5. Take the square root of 5, we get 2.2. And since this one is taller than it is wide, we're going to count up 2.2 units and count down 2.2 units and then name those coordinates wherever you land. The final skill you have to master is writing the equation for a given ellipse. So here's one graphed right there. I've given you the general format right there. But you can extract the amount of the same information that you could when doing them. So we have a horizontal radius of 3, a vertical radius of 5, and our center is at -3, 1. Let's write all that stuff down. So we have an h value and a k value right away. We set our horizontal radius, we count out 3, and we land. And we count out 5 in the up or down direction. So our a value, well, our a value should be 5, and our b value should be 3. But the number under the y term should be 5, and the number under the x term should be 3 to give us those appropriate radii. So if we do that, you'll notice that we have a 3 under the x term and a 5 under the y term. I've also substituted in an h value and a k value. Notice that the signs are swapped just because of the negative sign built into the formula. If you're asked to name the major axis, that would be this one. That would be the line x equals -3. And the minor axis would be the horizontal one at y equals 1. And then we find our foci points. So we're going to go 5 squared minus 3 squared to get 4. And once we have 4, we're going to count up 4 units and down 4 units from the center. So up 1, 2, 3, 4, down 1, 2, 3, 4. And we land at those 2 coordinates. I know this has been a long video already, but if you want 2 additional examples, here they are. You can draw a sketch of them real quick. And I'll just tap through the slides and talk about a couple things as we go through them. We need the basic information. We need center, horizontal radius, and vertical radius. So our center is at 1, -2. Our horizontal radius is 1, 2, 3, 4, 5. Our vertical radius is 3, so it's a very similar one to the last one. The equation, so the 5 is going to go under the x term, and that's going to be considered your a value. Your 3 is going to go under the y value. Right here, this one's slightly off center. So we have to count. This is 1, 2, 3, 4, 5, 6.5, and it's up 2 units, it looks like. So even if you have a decimal, don't freak out. This is going to go under our x term, and this is going to go under our y term. So our finished equations look like that. And if you wanted to find the foci for each pair, big radius minus small radius, take the square root of your difference there. And once you have that distance, count out from center. In this case, both major axes are horizontal, so you count left and you count right. And you come up with those sets of coordinates there. And for your homework today, you are going to do worksheet 9.1a, graphing ellipses. You're going to do problems 1 through 6. I think that's everything on the sheet. And you're going to submit responses to number 3, 4, and 6 on Schoology. I'll see you next time.